stresses actually. Are you able to define the stresses, or let's say, how do I define whether should I write it tau yx or tau xx, something like that? So we were talking in the last class something that because you so far is being taught to you stress is just tau and mu something. Some people write delta u upon delta y, some people write du upon dy, right? Something like that. But that's not a proper way to denote it, right? The proper way that you have to always define a this is in this particular format only, that here you have this the stress is actually have you have this is diodes actually, so this have two directions actually, so not only one, is two. One is the direction of plane and one is the direction of motion actually. The two things are being considered here. So can you tell me that out of these, what is first one, what is second one? If I write tau yx, what does it mean actually?
So tau yx, the y represents the plane and x represents the direction of velocity.
Yeah, so it is actually stress on y plane, and you are finding it's in x direction, okay? And whatever is plane thing, that thing should come always in denominator part here. And direction component is the velocity one, that should come on top always, correct? So this one is going to here and this y is going to this side, correct?
Yes, sir.
Okay, so if I rearrange this matrix in this format, let's say first I want to define only for x plane, so I would start from here. So I can take this here, let's say this tau xx, then I will say tau xy, uh, this one in y direction one, so I can write this one. Then tau xz, you have something here. So here you have defined everything for x plane now, right? This is uh, for x plane in direction x, x plane in direction y, x plane in direction z. Same thing you can write for y, y plane in direction x, y plane in direction y, and y plane in direction z. So you are actually going with plane by plane. So you can write this one. Then you have z plane in direction x actually, and z plane in direction y, and then you have z plane in direction z. So you have here for direction z, and then you have another one is for uh, so this is actually is practically this total is called the stress tensor, and you might have seen in your transport phenomena book. Have you seen this so far? Hello?
Yes, sir.
Yes, sir.
And Dr. Anurag might have also talked the same thing, right? Something like that, stress tensor. So this is called the stress tensor. Fine. So is it clear now how to define the shear stresses? So it's always a plane, then direction, Okay, so first one tau xx, tau yx, tau zx is all for the stresses for x plane. Then tau yx, tau yy, tau z, yz is it, that means stresses for y plane. Then tau zx, tau zy, tau zz are stresses for z plane. Okay, is that fine?
Yes,
Yes,
sir.
sir.
So that way your stresses need to be defined. So we can cut it from here. We can paste maybe on this one. So, so this is what we have defined so far. Now go back to your geometry. Now here you see in any of your 3D surface or 3D object have six surfaces always, right? Correct or not?
Yes, sir.
Yes,
Yes.
sir.
So it has six surfaces. So let's say this one is direction x. So this is your x plane. So if I just want to have here, let's say I can just copy it. So this one is it your x plane or minus x plane? What plane is this?
Explain, sir.
Are we plus x minus x?
Plus.
So plus x because here the perpendicular drawn on this surface is going to plus x side. So this is plus x plane. Now, if I go to this back one, this side one, and here the perpendicular will go to this side, and this would become your minus x plane. Okay,
Yes, sir.
Yes,
Yes,
sir.
sir.
fine. Same thing I can define for your top and bottom. So if I find for top one, so this would be your plus y plane, and same thing I can do for bottom one. So I can change this is minus y plane, and then you have this something for front and back. So this front one is your plus z plane, and your backside one, and this is your backside one, which you can define maybe somewhere here, is your uh, this is your minus z plane, correct? Right?
Yes, sir.
Now each of the plane you have three stresses, correct? As we have wrote here, that x plane have these three component. This mu du upon dy, and so you have tau xx, tau xy, tau xz. So let's see how to define all of them here on this particular plane actually. So here one thing is that plane is plus y, motion is also in x direction. You see this is the direction of the motion we have already predefined. So this is the motion of the direction, that this is motion in x direction, this is in y direction, this is in z direction. So here your direction of the plane is also plus, and second thing is what? How do you define that whether your shear stress or this stresses would act in plus side or minus side? So there the way to define the means direction of the stresses is you need not to worry about that how to define the direction something. So let's say whatever. So in this case, let's take this again. So if I am just talking, just delete all this thing. And let's say I'm just focusing on this. So first thing, I will calculate this. And do you know how to calculate du upon the dy? That means the nothing but you have that the simple mathematical thing. And now we are talking purely in the mathematical way here. So if you want to calculate du upon dy, is practically slope, and you are practically calculating either u2 minus u1 divided by your x2 minus x1. That's what we calculate your slope something, right?
Yes,
Yes,
sir.
sir.
So this is how we calculate it always. No matter how, either you can write this way, or you can also write, maybe you can interchange this, you can make this 1, you can make it 2, but it should be changed accordingly everywhere. It's not like that, that one where you. So in this way, both the way, your sign would not change. Either you calculate this way or you calculate this way, you will end up with the same sign. Correct?
Yes, sir.
Yes, sir.
Now, suppose this calculated thing for time being, let's say, let's this somehow for whatever the geometry is there, and let's say this has this calculated above somehow came plus. It can come plus, it can come the minus, right? Also, right? So suppose it came positive. Fine. This
Yes, sir.
thing came positive. Now, second part also, this is the magnitude. So this is purely the magnitude because mu is always plus, so it cannot change. This magnitude can come minus also, can come plus, depend on type of your flow, something like that. If okay,
Yes, sir.
so suppose this calculated value came plus. Now, next, this is called your magnitude, right? This is the magnitude part. If this magnitude came plus, now the next part is your direction of the plane. Direction of plane. And suppose this is also plus. If both the things are plus, I will tell you when will it be plus, when will it be minus. If both are plus, this magnitude and direction of the plane, if both are positive, then your shear stress would act in positive side only. No matter of where are you calculating it, you should not consider anything for that. So it will act always in this positive direction only. So if you are calculating for x-axis, it means it will act in positive direction only. So positive direction. So in this case, it will act in plus x side. Suppose these signs are not matching. Either this is minus or this is minus or this is plus, this is minus. In case if these signs are not matching, then so you can write if sign of write a magnitude and sign of plane are not same, then your shear stress would be in negative side always. One thing is that, so first one you came to here, that you can write this line also for this. If sign of magnitude and sign of planes are same, no matter whether they are plus or minus, then your shear stress would act in plus side, or if signs are different, then the shear stress would act in negative side. Is that fine?
Yes, sir.
This is how actually we have to always define the direction of the shear stress. You need not to adjust from your side कि okay ऐसा हो रहा है वैसा हो रहा है ये like this. It's not always. It's not like that. That's actually something you can say some jugaad techniques. So that's need not to be applied anymore. Fine. So this is where you will define your direction. Now, can you see that when will it be plus and all this? So let's go back to our figure. Now, let's say we are on this plane here, this one. So this case, your plane is plus x because here perpendicular will go to an x side. Now, if the motion is going to in plus x side, so obviously at this end the velocity would be more compared to this end because from here the flow is going to left to right. So left hand would have a high velocity and only the motion would always taking place to the lower side of the velocity. So as you will move from left to right side, your u1 would be high if you are talking 1 here. So let's say I can define something here in this way, two velocities here. Let's say this is u1 and at some time or some distance away this is u2. So I can write this is corresponding to x1 and this is corresponding to your x2. And these are the two velocities you have here. At point x1 you have velocity u1, point x2 velocity is u2. Is that fine?
Yes, sir.
Now, because the motion is going from left to right, so in plus x side, so u1 is always higher compared to u2. X1 would be low because from here the coordinate is just starting compared to your x2. Correct?
Yes, sir.
Then in that case, your u1 minus u2 would be a plus quantity divided by x1 minus x2 would be a negative quantity. Correct or not?
Yes, sir.
Right?
Yes, sir.
So on top you have plus, on denominator you have minus. So where would be the shear stress go? And so the magnitude will come your negative. Correct or not? So magnitude of shear stress which you will calculate from this expression here. This expression, if you will calculate that u1 minus u2 divided by x1 minus x2, this magnitude is coming now negative. Correct or not?
Yes,
Yes,
sir.
sir.
Yes, sir.
What plus x plane? Now direction of the plane is plus x. So your shear stress would act in negative side because the signs are not matching.
Yes, sir.
Correct or not? So your shear stress will act to the negative side. That and it means if your motion in this side, your shear stress would act in back side, and that makes sense because shear stress is the property actually given by your fluid. It will always try to oppose the motion. Correct or not? So if the motion is plus x side, shear stress would always means imparted by the fluid would be the negative side only because the fluid will try to resist the motion. Is that fine?
Yes, sir.
So that makes sense in that particular way only. So therefore, you can define your these components in that particular way. That how to define this one here. And now think about this side, because you are talking the motion is going to this side. So here now at the center, if the velocity is u, from where the motion is just starting. Now, if you will go to the back side by doing your Taylor series expansion, so here velocity would be slightly lower, because you will calculate velocity here would be mu minus del u upon del x into delta x by 2, because you have moved delta x by 2 to the back side. So you can find the velocity by Taylor's expansion. What would be the velocity here? What would be the velocity at the back side? So that's the another way, that how would you define the velocity? Do you know that how to define that? So I would show you some stress tensor here. So let me just open that picture again. You will understand. Where is that? Anything in between you want to ask? Is everything clear so far?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, one thing. So that's why is it taking that much time? I don't know. So, okay. Now can we use this? Both are hanged. Just wait, I want to show you something. Hmm. Let's say this one only. So this, because this is already a picture here. So in this case, you have your motion is just starting. This is the velocity at the center. At the center, velocity in x direction is u, y direction is v, and z direction is w. So if you want to calculate what would be the velocity at this particular end here, so you can do the Taylor series expansion to plus x side and minus x side. Do you know the Taylor series expansion, any one of you? Hello?
Yes, sir.
So with that, I can show you. So this is how you can calculate your properties to plus x and minus x side. So let's say you have some density at the center. So if you are going to dx by 2 to the plus side, so you want to say what would be the density at x plus dx by 2. So this is how it would be calculated here, that this rho plus del rho upon del x and dx by 2. You are not considering the higher order term, because you will have del square rho upon del x square dx by 2 to the power 2 and keep on continued for the Taylor series expansion, considering that dx is very low quantity, so the square term would be very low and all this. So you have just cancel all higher order term. You have just consider only first order one. So this would be Taylor series expansion up to first order one. So you got this is plus x side, this is to the minus dx by 2 if we went to the left side, and this is again to the plus side velocity, then this is one is minus side. Can you see this thing clearly? Because can you see this one? Velocity as x minus dx by 2. Can you see this
Yes, sir.
clear?
Yes, sir.
Yes, sir.
Okay, because my the display has some problem here. So then you got in plus by side and minus dy by 2. So this is how you can calculate your property from your Taylor series expansion part. So that's one thing. So same thing can be done for shear stresses. Let me see where that picture went. Yeah, this one. This one I just want to show you here. So let's say you have at the center of that particular block, where at the center you have the shear stresses is, now you might have seen there's some change here, sigma type of thing. So there's one thing here, the sigma, and other one is tau, right? So previously we wrote everything as tau, correct?
Yes,
No?
sir.
Yes, sir.
So what we did at that particular place, because there we are just writing the stresses there, so we just took a common symbol is tau there. So wherever your directions and planes both are same, then it will become a normal stress actually, because it will become the normal. It will not be no more the parallel to the surface. It is the normal, because if you will see the here direction is in plus x side, plane is also plus. So it will become a normal stress type, either for expansion or for contraction, either of that, correct or not? So in that case, this will become a normal stress which will try to either compress the fluid or expand the fluid. Therefore, the normal stresses is the defined by sigma. So wherever your directions and planes are same, you can change that tau to into the sigma, and that is known as normal stress. Wherever they are different, let's say tau by x or tau xy or something, wherever they are different, then they are treated as the shear stresses. That fine? So shear is always parallel to the surface, and normal stress always perpendicular, either to outside or inside. Fine.
Yes, sir.
Yes, sir.
So now considering, let's say shear means the stresses at the center is sigma xx here, and this is totally for only for x only. We are talking here for time being x1 only. Sigma x, then in y direction would be tau y x, because only plane you are changing. You are just finding in all the stresses which would act only in x direction. So if you are talking on this y plane, so y plane will have the again three stresses, right? Tau by x, tau by y, and tau by z. Correct or not?
Yes, sir.
So only tau by x will act in direction x. So you just took only that one only. Now same thing in the bottom side. So you wrote here tau by x. So that component which will act only in x side. This how this the minus came. This I will tell here. So at the center you just consider tau by x. So as you will go to plus upside, you are doing Taylor series expansion to dy by 2, because the total dimension direction by dy. So you moved downward by dy by 2 and upward dy by 2. Correct or not? So you moved plus delta y by 2 to top side if you want to reach to the top plane. If you want to reach to the bottom plane, you have to move down by dy by 2. Correct or not?
Yes, sir.
Yes,
So
sir.
Yes, sir.
therefore, you just wrote on the top, you wrote tau yx plus this delta yx upon del y multiplied by dy by 2. This is at the top plane, top y. Minus y, you just put a minus y because you want to expand it to the minus side of the Taylor series. So you got this value. Now you can see this sign. This sign is to this side and this sign is to in plus x side. So why it is so? Because this total quantity here is plus. Hello? This because your actually the direction of the motion is also plus. Direction of the plane is plus y. So both are plus. Therefore, the sign you have taken to plus side only. This one is plus. Fine.
Yes,
Yes,
sir.
sir.
Now in bottom side you see sign is the reverse. Why is it so? Because this total quantity again, because you want to calculate everything in direction x means plus x side. So your the direction is fixed plus x. Only thing here is plane is this minus y. So therefore direction is plus, plane is minus y. So both the signs are not the matching. Therefore this is acting in to negative side. So this is the direction of the shear means stress on the bottom plane. Okay.
Okay, sir.
Yes, sir.
Yes, sir.
Now you see for this one, this side for the x plane, direction is x. Direction of the plane is also plus x. So therefore the sign is into plus side. This side, direction of motion we have considered to plus x side. So that is plus. But direction of the plane here is to minus x side. So therefore the sign is into the back side only. Fine.
Yes, sir.
Now for this plus z plane, direction is plus, plane is also plus, so therefore the sign is to the plus side. Go to the bottom side, means back side of this particular the monitor. In that case, the direction of the plane is minus z, but direction of the motion is plus x, so the signs are opposite, therefore it will go to the opposite side. So therefore these signs are the fixed in that particular pattern. Is that fine?
Yes,
Yes.
sir.
Now these are the stresses only in x direction at all planes. Plane top one, bottom one, front, back and left and right. These are all the 6 stresses only in x side. Now can we do the balance? What should be the total stress in plus x side? So we can add them up, correct or not?
Yes, sir.
Yes, sir.
What would
Yes, sir.
practically we want to do the force balance. So if you want to do the force balance, just add all forces in x side. So let's say you want to do the force balance. So what is force? Force is practically rate of change of the linear momentum, correct or not?
Yes, sir.
Yes, sir.
So that is
Yes, sir.
the definition of the force is being taught to us. Now you can write linear momentum further, the mass into velocity.
Yes, sir.
Now this mass, if you are talking about the differential mass, so you can write a dm or the differential force. So you can write d everywhere, let's say df here, dp here. So in that case, if you want to calculate the differential force, and force ka you have the another formula also, that mass into acceleration also, correct or not?
Yes, sir.
Yes, sir.
So that would be df would be dm upon da. Practically, this is your da, acceleration differential means acceleration. So acceleration can be calculated by dv upon dt. Correct or not?
Yes, sir.
Yes, sir.
Now your velocity vector has four component. Direction of the means velocity in direction x, velocity in direction y, velocity in direction z, plus a unsteady state component due to time. So therefore, its total derivative can be defined in that way that u del b upon del x plus v del b upon del y plus w del b upon del z. So these are all velocities or derivation or derivative in direction x, y, z plus there was a component which was purely a function of time. So that is again del b upon del t. So this is total derivative of your velocity vector. Okay.
Yes, sir.
Yes, sir.
Yes, sir.
Now you would be confusing how this x came here, how this u came, because you are the writing here dB upon dt, and now you got x and y here. Correct or not? Or is it clear to you?
Yes, sir.
Is it clear that how this came this way, or shall I uh, means elaborate that?
Can you
Hello?
please elaborate?
Yeah, yeah, that I am thinking. So that way, if you want to write here, so practically this was your velocity vector. Let me copy it complete. So this is what you have. Practically, you want to calculate your dv upon dt, right? This is what you want to calculate. Yes?
Yes,
No?
sir.
Yes,
I
sir.
can write it in let's say total derivative के definition के format में. Now, because I want to calculate it, so what can I write here? I can the write because this have a component x, y, z, and t, right or not?
Yes,
So
sir.
I differentiate this one, my velocity. I can write first thing I can define it with respect to x, and if I just change this component by x, I will get the first thing which I want to write dv upon dt, right? From here.
Yes, sir.
Because dx will get cancelled, right or not?
Yes, sir.
Yes, sir.
Same thing I write for that. So I here I can just write y and this also y, and another thing I can write for this. So this I can write here z, and this is also z. So I got for x, y, and z, and a component. There was a component only for velocity with respect to time. So I just wrote for this as it is only. So this would be my total the derivative of this. Now, what would be this component? Dx upon dt, distance travel in direction x divided by time. What is that called? X direction
U.
velocity.
Yes.
Yes, sir.
Yes, sir.
So I can write that in that way. So I can write the first one would become u. So this term has went away. Second term from here dy upon dt would become your v. So I will get y velocity component. And next one here I will get here w. So it will cancel from here. And last one is your time as time. So you have that. So this is your total acceleration of the particle. Is that fine?
Yes, sir.
Yes, sir.
So that's way you got that particular expression there. Now let's go back there. So So you got this. So this is the total force. Now, if you want to write these forces in direction X, direction Y, direction Z, so what I put here, I just change something. Only change I put here, X laga diya only. Because this was the differential, 1 minute. So this was the total differential force on this, the differential element. Now, if I want to calculate force in direction X, so I put here dfx. This dm is fine. For to you, dm is the differential volume, dx divided dz multiplied by density is the differential mass. Is that fine to you?
Yes, sir.
Yes, sir.
Now from here, so I wrote for x1. So x के case में only you have, this is the thing which is the velocity vector. If I just write this velocity vector in direction x, I will get the x direction component of velocity. So all velocity vectors, this v vector here, this one, and this one, I just put here u, here also u, here also u, here also u. So this is my net force only in direction x. Same way, if I want to write only for direction y, I change this velocity vector here by v, here also by v, here also by v, here also by v only. Now same thing for z directions. So w here, w here, w here, w here. So these are your forces in direction x. This is direction in y. This is direction in z, and this is the total force. Is that fine till here?
Yes, sir.
Yes, sir.
Fine. Now let's go back to next one. Now that previous one was totally from force balance. Force is practically nothing but mass into means acceleration. No matter from where the force is being exerted and all this. Now go back to your picture. Your figure is this. This is your differential mass, and here if you will apply a force, this would be its condition, something like that. Correct or not? At all six surfaces. Now I would add up all these forces in direction x and I will balance the two. Correct? Because these net forces will give you me the net force on this, which will give some acceleration. Correct or not?
Yes, sir.
Now that's what is being done here. Here dfx fx fsx means surface forces in direction x. Because forces can act only on the surface. Internally it will not. Correct or not?
Yes, sir.
So direction x, so first one was plus, so I wrote here in direction x1. Left side one was the minus, so I put a minus sign here, so that would be net force in direction x. Same thing for top plane, it was plus, bottom plane it was a minus sign, so I put a minus here. Then this is your front one, and this one your back one. So this would be your net forces in direction x. Correct or not?
Yes, sir.
So if I simplify this, so this first term will get cancelled. Second term would be added, and you have half here, it will become full. Correct or not? So in all these first term, sigma xx, tau by x, tau zx will get cancelled by this term, this one, and a half term would be added up, they will become full. So it will become something like that. dfx would be equal to sigma del sigma x upon del x, del tau yx upon del y, del tau zx upon del z, right?
Yes, sir.
Previously, you just, and this is your practically is your area. Dy into dz is the area of this plane, dx upon dz the area of top plane, and in the bottom plane is the front plane. This one is the area of your z plane. Correct or not? So shear stress stresses multiplied by area is just force only. So if you add that, this would be your differential force in direction x. Now this is the surface forces. Now ev- every body would have some weight, right? Its own weight. Its own weight is what? Practically the mass into density into g. Correct or not? Hello? Hello?
Yes, sir. Yes, sir.
So right, so you would have a body weight also. Body weight would always would be the body mass multiplied by g is called body weight. Correct?
Yes, sir.
Response part. Now you want to calculate only for x side. So this body mass is not action by component. Mass is just mass. If you will multiply by gx component of g in direction x will give me the body weight component in direction x. Whether gx is there or not there, zero or non-zero, that is a different task. So I just multiply here by gx component of g in direction x. This would be my your body weight in direction x. Correct?
So could you please explain this part again? So the body weight.
Every material have some weight. Correct or not?
Yes, sir.
That's called body weight.
Yes,
Now,
sir.
if you want to calculate it, multiply by a component of g in direction x, you will get body weight component in direction x. If you multiply g in direction y, you will get the body weight in direction y. In body weight in direction z. So only thing mass, this is the mass component first. Rho into dB is mass. Multiply by g is body weight. I want to calculate only in x side, so I just multiply by component of g in direction x only. That's all. Is that fine?
Yes, sir.
So this is the body weight component in direction x. Same way, if you want to calculate for direction y, I just multiply this by gy only. If I want to calculate direction z, I will just change only by gz here. That's all. Okay. So these are the two forces would will act on body, the surface force and body weight. These would be only two forces that particular differential volume would have. Is that fine or not?
Yes, sir.
Right. Now, if I want to calculate total force in the direction x, so total the surface force in the direction x plus total body forces in direction x. So I will add these two. So first one, second one. So I will add this one. So this is coming from here. This one is coming from body weight. And this total force is the same, which I just calculate from here, the mass into acceleration part. Correct or not? Right?
Yes, sir.
Yes, sir.
So I would get this expression that rho del dx divided the dz multiplied by acceleration in the direction x would be equal to the body weight, body force, and this the surface forces. Dx divide dz will cancel from here. You would end up with this equation actually, that rho u del u upon del x, v del u upon del y, w del u upon del z, and del u upon del t would be equal to rho gx plus del sigma x upon del x, delta of yx upon del y, delta of zx upon del z. So this would be your x component of x momentum balance. This is practically is just x momentum balance. We are not saying it for time being. Naves stock equation, we are not saying it now because it's not here. It's just the x momentum balance. Okay.
Yes, sir.
Similarly, we can write for y momentum. So y के लिए only this would change y v. This is also y v. This is also y v. This is also y v. This x would change by y, and these coordinate will change. Last coordinate, this x would change by y, this also by y, this also by y. Only your direction is changing to y direction only. So in that case, you would end up with, this is your x component, this is your y component, this is your z component. So today we came to your x momentum balances, y momentum balances, and z momentum balances. Correct?
Yes, sir.
Yes,
Hello?
Yes,
sir.
sir.
Now I
Yes,
would
sir.
just give you some homework to that. That these are the just the momentum balances. Can you somehow find the equation sigma xx and tau yx, tau zx for Newtonian fluid, and substitute the expression here, and let's see what is coming. Simplify only this term, these three terms only for Newtonian fluid. Okay? And we will end the class there. So I would just give you some hint to you. Newtonian fluid, your tau yx or tau xy is given by this. Zx or yz is given by this. And zy is given by this. Sigma is given by these expression, that minus p to 2 by 3 mu del dot v, and this one. So you have everything. Substitute there and try to get the equations, and whatever will get by substituting that would be known to you as Navier-Stokes equations. So we will
Okay,
end
sir.
the class here. Try to do that, and let's see what will you get. In case of the doubt, you should actually can contact me anytime. Don't wait for the another class.
Okay, sir.
Okay, sir.
Fine. हाँ.
Yes, sir.
इसको solve करके you would end up with this one. This is known as Navier-Stokes equation, given at the back of your transport phenomena book.
Okay, sir.
Okay. So yeah. So try to do that, and we will end the class here. If you have any doubt, anything, you can ask now.